If any questions on the problem sets first, I'll always take. So here's our formulas. Here's our formulas in general from all of chapter 6. These are all on your formula sheet. Everything on here is on your formula. If I forgot something, let me know. Oh no, elastic energy. Right? The other potential energy is this. Okay, sorry about that. That's everything from this chapter. Okay, Chris?
Wait, if X doubles, then P quadruples, right?
Then PE would quadruple, yeah. Very good.
And then if K doubled, then it would just go up by a factor of 2.
Yes, that's correct. Okay. If something doubles or triples and it's in a square, you square whatever that effect is. So if X were to triple, or hypothetically, if the velocity tripled for the kinetic energy, it would go up by 9. You would square it because you put a 3 in here. You're technically squaring the 3.
Yeah.
Yep, very good. So these are directly related, right? Kinetic energy is directly related to mass. Potential energy is directly related to mass. That makes sense. More mass, more energy. But the kinetic energy is directly related to the square of the velocity. So that's why, as Chris mentioned, if you triple the velocity, you would increase the kinetic energy by a factor of 9. Because triple squared is 9. 3 squared. All right, sorry about that. So let's continue with questions. Questions?
Kind of a general one for
Yeah.
kinetic energy stuff. How do you know what to set to 0?
Okay, so it depends on the situation. So for example, if I had a situation, we could just do a couple situations if you want, because that might be the best way to practice for this. Sorry, did I move everything off? Do we have most of it down? Can I move that a little bit? All right. So if I have a scenario where, I don't know, you have a spring compressed somewhere, or you pull back on a rubber band, those examples, or you wind up a toy car. Ever see little toy cars? You wind them up, put them down, and then they go. When you wind them up, what are you doing? You're storing elastic energy in the spring. It's a rotational spring. So in a problem like that, your MEI equals MEF simply would become PE elastic in the beginning. Because that's what you're doing. You're literally turning a spring below the car to give it elastic energy. Now, bless you. It's a stored energy, hence potential. Potential has to do with it being stored. Now, if this little toy car, take a look up here, were really this calculator, and I placed it on the table, and it was going to drive, God bless you, off the table. I placed it on the table, I sprung it up, so I gave it elastic energy. When I release it on the table, it has another type of energy also. Because it's on the table. What type of energy does it have?
The regular potential energy.
Yes, the regular potential energy. That's what it would have in the beginning. So this is a toy car sprung, or whatever you would call it, not sprung, wound up, placed on the ledge of the table. Now, yes, it's going to start moving. And where is that motion coming from? Where is that motion coming from?
Well, the
spring. So the motion is not occurring at the same time that the spring is fully wound up. Do you see what I'm saying? So in the beginning, there isn't any kinetic energy. Yes, in a moment, it's going to start moving. But right now, when it's fully sprung, when it's fully wound up, it is not moving. That's a very common misconception, okay? Because students think, oh, it's going to start moving. It does start moving afterwards. So eventually, it's going to have velocity. Right before it's leaving the table's edge, now it's moving. It's still partially sprung or wound. Jeez, I keep mixing those words. Wound. And it still has a height. So if we're looking at the situation where right before it leaves the ledge now, we would have these two energies and kinetic in addition. Then it eventually leaves the edge of the table. It falls to the ground. Right before it hits the ground, if we want to figure out the terminal or the impact velocity when it hits the ground, it would only have kinetic energy at the end of that problem. So if I consider after I've wound it up and placed it on the table as initial, and then hitting the ground final, All the energy in the spring has caused it to move. Let's assume the spring is falling around right now. It has fallen a certain height, so it has no more height. So these two are gone in the end. And since it's moving, when it's about to hit the ground, the impact velocity, it would have kinetic energy at the end. So again, Christian, to answer your question, it depends on the scenario. This is one scenario that I just gave you. How about another scenario? You come up with one. Give yourself, or somebody come up with a problem, present a problem having to do with motion, having to do with height, having to do with energy. And think about what energies it has along the way. So think of a scenario. What scenario can you think of right now? Come on, you guys are creative. Use your creativity. What scenario can you think of that involves height, motion, elastic energy? Think of anything. Use sports, use things like think about the backyard, or like any sort of leisure activity that involves motion. Yeah, that's about it.
Jumping off a diving board into a pool.
I like it. Jumping off a diving board into a pool. All right. The diving board has what kind of energy when you bounce on it? Elastic energy. It also has height. And then when you're going to hit the water, you have kinetic. So it's the exact same equation. Isn't that wild? Think about it. You can spring, so wind up the car, place it on the table, and let go. And that's the equation that represents the motion. Elastic and height, and then motion at the end. If you're on a diving board, it's the exact same equation, identical. But K is now a different spring, right? You're not winding up a rotational spring anymore. It's like a linear spring, or a fin, you call it a fin, a cantilever beam. So that spring energy is on the board, your height is there, and then you hit the water, call the surface of the water ground level. So when you hit the water, you only have kinetic energy. Eventually, what does the water do to your body? It causes you to stop, right? The water is like friction. So if you want to consider the water also, and find out how far you sink into the water, D, you can find Q loss on the end. Remember Q loss? If there's friction along the way, you have energy loss. So if you think about when you hit the water as energy loss, you could say, you're going to lose a lot of this energy. And then you could figure out the work done by friction and replace that with the force of friction times D, times cosine theta. And you could progress through this problem and find out how far you sink into the water if you know how much friction the water presents, so it gives you. You have to be given that value, though, right? You don't know that number. It's not like it's mu Fn. You can't use mu Fn when it's water friction. It's viscous friction. So I have to say the friction provides a force of 10 newtons. That goes right there. This is always 180 when it's friction. And then you can solve for D, which is how far you would sink into the water. And D is the distance that friction acts on your body. And it's only when you're in the water that the friction of the water starts acting on your body. So, again, picturing this, your body hits the water right there. That's the impact velocity. So you have some kinetic energy right there. That's where you have kinetic. And then as you travel into the water, you're going to lose energy. This is the distance D that we're looking for right there. And Q loss is that energy loss after you hit the water. I'm just trying to give you guys different presentations with this idea. How about something with a different equation? I saw other hands go up when I asked for scenarios. Isabel's happened to be the exact same scenario as far as the equations themselves. What's another scenario? Sophie, you kind of had your hand up. Rodrigo, you were thinking about something, or one of you guys in the back had like a hand going up. What are you thinking?
I was thinking a roller coaster.
Yeah, that's a great example. So a roller coaster, if we study a roller coaster's energy, you want to start at the top or the bottom? Start at the top or the bottom?
Bottom.
Okay. I'm asking you because I want to show you that it doesn't matter what you choose, right? So the problem is up to you to decide, and then we'll investigate. So let's say the roller coaster starts at the bottom right here. Okay, it's got motion. Maybe it just came off of a loop-to-loop, and it's going to go back up. So at this point, it has kinetic energy. If I call this ground level, it makes sense. Can somebody repeat or explain why again we call that ground level? Chris?
This is Y 0.
Yeah, whenever this is the bottom value or the lowest, you want to call that Y is 0. The lowest value, call Y equals 0. So every height along the way will have some height to it. So as this object, this roller coaster cart, travels up, what kind of energy does it have? Well, here it's got kinetic still because it's still moving, and it's got potential. And it's got potential because it's gaining height. If at the top, hypothetically, it creeps up and it stops at the top and it's waiting to take off up here. Okay, it's waiting to take off. What kind of energy does it have? only potential here. Assume it stops. Okay? I'm telling you it stops. And if you think about a roller coaster, right? At the very end, you usually come back up to the top really slow. You get to the top and it doesn't wait. And this is sad, but I've never been on a roller coaster. Really sorry. I get really motion sick. But since I've been a kid, like, I love rides. Don't get me wrong, and I've gone on a lot of rides before. But like roller coasters and things that spin in circles, which are a lot of rides, I know, make me like ridiculously sick.
How do you do it?
I've thrown up like 10 times in rides in my life. I keep trying it. As I get older, I try to. Even like airplanes, I get really motion sick. Boats were bad for a long time.
Really?
I'm good on boats now, thank God. I never used to be able to go on a boat.
Well, maybe you just need to practice on the roller coaster.
It's like I've thrown up on people before, like a lot of times. Yeah. You know the Ferris wheel? The Ferris wheel on its side was called the parachute. Did you ever go on the parachute before?
Yeah.
That one was the worst. Because I threw up and it hit the next couple carts behind and everything. I was like 10 years old. True story. I wanted to be an astronaut when I was a kid, and then I found out that I couldn't go on rides and have any motion, and I was like, probably can't be an astronaut. Yeah. Anyway, so does it stop at the top, right? It usually stops, maybe?
Yes.
All right, before you hit that like descent, maybe it makes sense to give you that like you're thinking about falling. Anyhow, so that's the idea here. How about this? What if eventually, right? What if eventually this roller coaster's brakes failed? I know, right? And there was a safety mechanism in place at the end of the roller coaster, and there was this giant ball of hay, or giant area of all this hay. And the roller coaster hits the hay and comes to rest. What would you consider that to be then? And I drew that shape for a reason.
Spring.
Yeah, that'd be a spring. Okay, anything that slows the motion at the end or involves some sort of an absorption of energy there because of its deformation of its shape, even something like, honestly, like hitting into like a fluid like water that would slow it down. You could model it in a sense as a spring. It doesn't behave the same, fluids and springs. But you could think of it as PE elastic at the end. Okay, that would cause it to eventually stop at the end. So it would have all elastic energy at the very end. On the way down, though, again, it would have potential and kinetic still, right? Because now it's moving and it has that. So this is what you need to be considering, right? Being able to label any point in the diagram. Now, let me follow up with a question, because this is the part where people get the most confused on the math parts. If this problem is talking about takeoff, lift off, whatever, and when you get to max height, do I care about this in the math parts? What do I do? What do I have to do to the problem? I keep talking about this. I say, with the problems, you have to do something to them. And this is the part that I think people actually make mistakes most. You have to do something to the problem.
You like split it?
Yeah. You need to break the problem into pieces. So if the problem is only referring to the beginning up until it gets to maximum height, that's the end of the problem right there. But then maybe part B says, after, this is like an AP level question, really. I could give you stuff with A and B that has different parts, it'd be a little easier, but it might say that after it reaches the top, it then starts to fall, and maybe there's friction. You have to incorporate work done by friction, FD cosine theta, if you can find this distance. This would be like a hypotenuse distance if you think of a triangle. Okay, this is a triangle right here. Okay, that's like a hypotenuse. You can think about the friction being done. So you know what? For that kind of a problem, even though earlier this was the end of the problem, right? That was final. Back here, this was initial. Well, you know what? For part B of the problem, maybe this is now the beginning of the problem, and this is the end of the problem. So you need to be ready to break your problem into pieces depending upon what's being asked. On the way up, and then on the way down. On the way to the right, and then back on the way to the left, depending on what you're doing for the problem. Okay, I'm presenting that as a hint, okay, just so you recognize that you're going to definitely have to break up a problem into pieces. Great question.
I'm sorry, when you say break problem pieces, there's always going to be two pieces.
There could be 3, 4 pieces, whatever. It doesn't matter. I could have A through D. The object slides down a ramp, then goes in a little loop-to-loop, then, like this is later in the year, you could see more of this. Then catches onto like a pendulum, like a rope that flings off, goes through the air, hits the water, slows down. You have like different segments along the way. Okay, it's like, have you ever seen a Rube Goldberg contraption where it's little pieces along the way that make an end result?
Oh, actually, yeah.
It's like that in your mind. You have to break it into different segments. And when you're doing this, yeah, the energy balance is always the same, but you have different segments and pieces along the way to solve for different pieces.
Right.
Yeah? And you can involve energy with kinematics. And the next chapter we'll do momentum, and you can involve that with several parts of the same problem. Specific problems on the problem set. Specific ones. Chris, go ahead.
Could we do 103?
103. What page, Chris? Do you have it?
Yeah, 222.
Thank you. Got it. Thank you. All right. 103. It says a 0.26 kilogram rock is thrown vertically upward from the ground to a cliff that's 32 meters high. When it hits the ground, from a cliff, right? Yeah, from a cliff that's 32 meters high. When it hits the ground at the base of the cliff, the rock has a given speed of 29 meters per second. Assuming that air resistance is ignored, find the initial speed of the rock. That's part A. Then this is exactly what I'm talking about. So this is a great example. Then part B says, find the greatest height of the rock as measured from the base of the cliff. So you need to think and visualize. This is the problem right here. It's thrown vertically upward, so assume it doesn't go out at all. Assume it does not go out at all. In the beginning of the problem, it's thrown vertically upward. So what kind of energy does it have? It's thrown. What kind of energy does it have? What energy is that? When it's moving, you're throwing it. Come on, Joe. Which kind of energy involves motion, Joe?
Be kinetic.
Kinetic. There you go.
Yeah, sorry.
It's all right. And it is an applied force you apply, right? You're doing work. You're applying a force, and that force and that work done, Joe, causes kinetic energy. That's where you're giving a kinetic energy. But you are applying a force. That's right. It's at a height of some value, 32 meters in this case. So what other kind of energy does it have also? Yeah. It's got to have potential also. Okay, and that's right here at the starting point. Now, we are concerned with when it hits the ground, we are given a velocity, right? So let's call that the end of the problem. For part A, again, for part A, at the end of the problem, we can say it only has kinetic energy. The potential is gone because it loses height. Part B has to do with maximum height. It says how high can it get? So we'll talk about that part of the problem next. So right now, because part A is only focused on the beginning and the end, I ignore the middle. Okay, I ignore the middle. So in the beginning of this problem, we know again, MEI equals MEF. It's the same equation every time. Now, it says that air resistance can be ignored, so I'm going to do that here. I'm going to ignore it. I will incorporate it in a minute and show you how it can actually be used. So for now, the initial energy is potential and kinetic. That's what it has at the top of the cliff. And here at the bottom, it's got just kinetic energy. This is where I start applying subscripts because along the way, it helps me to keep my values organized. When it's in the diagram, I don't really need subscripts because I know what I'm talking about there. Okay? I replaced these with formulas. This is the easiest part, right? You're literally just looking at your formula sheet and replacing the formulas with the correct things. You don't have to have this memorized. By now, I'm sure you do. But you don't have to have them memorized. Did I need to give you the mass in this problem? Was that necessary? Or did the book need to give you the mass? Was it necessary to give you mass? James?
No.
How come?
It's in all terms.
Whenever, write this down, please. Whenever a problem doesn't involve a spring, I should say elastic energy, when it doesn't involve elastic energy, or Q loss, work done by friction, mass will drop off. Again, because mass is in everything except for elastic energy and Q loss. Sometimes mass is in Q loss, and we've seen that before with the extra credit, with the sliding of the socks. The mass canceled there because the force of friction was mu mg, so mass canceled. So sometimes Q loss has mass in it, but whenever you have a spring or elastic energy, you can't cancel mass. And the Q loss usually presents an issue as well. So remember, canceling mass here is because we don't have those other things. And also because you just literally look at it. Mass is in everything, so it drops off. I'm literally dividing the whole equation by m, and they're all gone. Chris, you look
Wait,
at
if
the
you
other
don't,
question.
if you don't cancel mass and just do it normally?
It works, yep. It works, absolutely. But Chris, I'll hint at it now. You're probably going to have a problem on the test where mass isn't given in the problem. What can you most likely assume is going to happen?
It's dropped, they drop.
Yep. That's a good indicating factor there. You see what I'm saying? If you guys go on to take the subject test in physics, those problems are given in such a way, by the way, they're all multiple choice. It's like a 50-question multiple choice. All the math problems are in multiple choice. The problems are given in such a way that cancellations help you to solve. They're not going to give you the mass. They're not going to give you certain values that drop off in the equation. The same thing goes on for AP Physics. Okay, either of those, the tests or that. I'm trying to prep you for that because I know some of you will. Our goal is to figure out with what speed should we throw it. That's the question. We're told that the height of the cliff, which is the initial height, is 32 meters. And we're also told that it lands with a velocity of 29 meters per second. So my givens are at the top left there. I'm going to plug them into the equation if I want to now and solve for VI. Or solve for VI first. It's totally up to you guys. You can do whichever you want. I'll show the steps for those that like to see it. So I would start by subtracting GYI. GYI is a term. This is a number, right? G is 9.8, Y is 32. This would be a number. I would take this number and subtract it from this number. So I'm literally going to do that. I'm just going to move it over with variables. Then I'm going to multiply by 2. And then I'm going to take the square root. This is the same exact equation you would get if you used, instead of energy, if you used kinematics from last chapter, or a couple chapters back. I'll do it in yellow on the side. You could have used this. Right? And then solve this for VI. Take a look, okay? So if you see in yellow, I'm showing you how we used to do with kinematics. With kinematics, this is the equation. You want the initial velocity, you've got the final velocity, you've got the displacement, you've got the acceleration. This is just g. This becomes 2gy. There's 2gy. Vf squared, vi, vi. It's the exact same answer. Isn't that beautiful? Like, you think about it, kinematics and energy, completely different things, come up with the exact same solution. Simply because this object is only working in one-dimensional motion. That's the reason. Okay? It's only because it's going up and down. If you want to add an angle, you'd have to consider more of that. But again, that's just a side note in yellow. I just wanted you to see that. So this kind of a problem, that's your answer. Okay, you would plug in your numbers to get your VI value. This was 29 squared minus 2 times 9.81 times 32. Whatever that turns out to be. That's a 29 squared. This is number, again, 103. Does that answer, Chris? Does that help?
Yeah.
For part B, it says, find the greatest height of the rock as measured from the base of the cliff. So where's the greatest height? Well, it's at the peak. So let's go ahead and call that now part of our problem, right up here. And at this point, it's only got potential energy. At the top, it stops. At the top, it stops. If I am kicking a football or a soccer ball, and I'm kicking it at an angle, and it goes like this, ready? Does it stop at the top? Because it's always moving which way? It's always moving to the right. It stops vertically, yes. It's going up, down, down. So it's got to stop vertically, right? But remember from kinematics, Vx is always a constant, isn't it? There's no wind resistance, there's no horizontal acceleration. So when it stops, when it gets to the top, in projectile motion, it still has kinetic energy. This is not projectile motion. This is launched straight up and coming straight down. Is that clear what I'm saying right now? That's why there's no kinetic energy at the top there. It's only potential. So for this part of the problem, we're trying to find out the actual maximum height itself. Well, you know what? Now we can do it either way. We can find the energy in the beginning instead of equal to that, or find the energy at the end instead of equal to that, because energy is conserved. Energy is conserved, conservation of energy. So I could say the energy in the beginning is potential and kinetic, and that's going to equal the energy at the end, which is only potential. So now I am literally doing this. Watch. Once I've done part A, I'm getting rid of all this. I'm only looking at the first half of the problem, from when it's launched to the max height. Here's when it's launched, here's max height. Obviously, I'm going to have to use VI from this. I'll use the number we got as an answer to actually do the math here. But this is my new equation now for part B. The PE in the beginning is mgy in the beginning. The PE at the end is mgy at the end. The KE in the beginning is 1/2 mvi squared. Everything is known on the left-hand side. Everything. You know these values. They're both known. 32 and VI is whatever you get from this right here. That goes in. The M drops off everywhere. Solved for YF, the final height. The height at the top of the path. YF again. Here, I'll draw it on the diagram. I try to use red. This is YF. Okay, that's YF. I'm sorry, I should actually draw it all the way down. YF would be the entire thing. Right here. Because YF is the energy at the top, and we called this ground level earlier, so this is still ground level. So that's got to be your YF. Plug in numbers and solve. Again, mass drops off in all three spots. Side 103. What else? There were a couple others you that asked earlier. Didn't you ask about one? Somebody in the front asked about, right? Was it you?
I just have like a question mark problem. So the PEF would be 0 because it like makes it to the ground. So at the ground level, the PEF would be 0.
The VF? This VF would be 29.
No, the PE.
Oh, PE at the end would be 0. But this is not... What is F? F is the end of the problem for the second part. And the end of the problem is the top of the path. So this is not equal to 0 here. The PE for the original problem was 0. Watch. Go back over here, okay? Follow the cursor. As it goes across here, if I consider this the end of the problem, then PE is 0, which is why it's not here. See where I'm pointing? That's why there's no PE right there. It's 0. But now for this part of the problem, Rick, I'm looking at, ready? This is the beginning, going up to the top, and that's the end of the problem right up there. So at the end of the problem, which is right up here, it still has potential energy. That's this energy right here. If something is 0, I'm not going to write it. You follow what I'm saying? When something doesn't happen, like there's no kinetic energy at the top, right? Because it stops. So I didn't write kinetic energy. So if I'm writing it because it actually exists. So when you go to use this equation, this is the generic equation, or the governing equation right here. But all you're going to do is fill it in with what exists at those moments. Yeah? You sure? Okay.
I don't remember.
A 1.3 kilogram block is pushed up against a spring, compressing it a certain distance. The block is released. The spring pushes it away across a frictionless floor. What is the speed of the block, given that the spring constant is a certain value? All right, so this is a problem, again, of transfer of energy, right? Here's the block. Here's the ground. When it's released, the object eventually starts to move like that, right? So, when it's compressed, what kind of energy does it have? There's the word compressed. What am I saying? What's compressed? What kind of energy? Come on. Every hand should be up at this point, guys. When you hear the word compress, what kind of energy is it? Automatically. Joe, what kind? Potential. What specifically? What kind of potential, Joe? Because it's compressed or stretched. Elastic potential energy. Elastic. It's elastic. Elastic has to do with stretching things, right? When things are stretched or compressed, we write elastic potential. James.
Is it strictly elastic, or can you say PES too?
PES is fine. If you call it PE spring. Yep. As long as you use the formula later on, 1/2 kx squared, I'm totally fine with that. Now.
So PE and PES are the same.
PEE and PES, yes, are the same thing. I think on your old text it was PES, and the new one is PEE, so I've been changing it, but it might not be the same on your formula sheet. But the idea is that you're going to use 1/2 kx squared. Now, it's released from the spring, right? The spring, is anybody picturing what this is right now? It's a pinball machine, right? It's a pinball machine really, except flat. Pinball machine, when you pull back, it's usually at an angle, right? And the ball is fired at an angle, which causes the fall. Pinball machines, by the way, are the best example of inclined planes. A pinball machine is just an inclined plane. The ball uses gravity to fall. That's all it is. So your spring is giving it energy. You let go of it, and now the pinball gets released. It's moving. In this case, it doesn't even gain any height. So we don't have to worry about potential energy at all in this problem. At all. No potential energy problems at all. Height potential energy. Obviously, elastic. What kind of energy does it have because now it's moving? Kinetic energy. So if I call this the beginning and that the end, I could say in the beginning, it equals the end. In the beginning we had spring energy. At the end we have kinetic energy. Spring energy is 1/2 kx squared. Kinetic energy is 1/2 mv squared. The 1/2's on both sides, I'm going to drop it. I get kx squared equals mv squared. The problem asks us to figure out the velocity of the block. Everything else is known. Your units need to be changed though, okay? Just be careful of your units. That's the hint I'll give you at this point. The K units are newtons per meter. The units for the distance it was compressed, which is called x, was 4.2 centimeters. Right? So x was given as 4.2 centimeters, so we have to use 0.042 meters. The K was given as 1,400 newtons per meter. And mass was 1.3. And remember that kilograms are the base unit. You don't have to change that. Just go ahead and plug in. Can I ask for the follow-up question? How about this, okay? Follow-up question. Eventually, after moving for a little while, right? Follow-up. After moving for a little while, the block object encounters a frictional surface, okay? It encounters a frictional surface. Did anybody get a number for this, by the way? Do you have the right number? Can somebody just what do you have? 1.48. I don't know if anyone calculated it. Did anyone get this for this one? This is number 105. Number 105. If you're just looking at your problem set. Did you get that?
1.37.
You got 1.37.
So did you go?
I'm calculating.
For 105?
Yeah.
1.37 meters per second.
Did anyone else get an answer for 105?
At 1,400 times 0.042 squared over 1.3.
1,400 times, go ahead.
0.042 squared.
Got it.
Over 1.3.
And the square root of that.
And the square root of that was...
Did you take the square root of that, Isabel?
Yeah, I think
I just got 1.4.
I
He got 1.48. All right, we got two at 1.48.
1.37.
Oh my God, kill me.
I got 1.37.
It's 1.37. I actually, like, when I did it, I took it and I moved it 1.3. I don't know why I did that.
No big deal. No big deal. All right, so we got 1.37. Perfect. Now, that's the velocity that the block has. My question for you is going to be this. Ready? If the mu value, the coefficient of friction on the floor, so let's draw this so we can see it, okay? Suddenly, it encounters part of the floor that has friction on it. We'll just put that for friction. If the mu value of the floor is 0.15, determine how far it will go. Determine how far it will go. Now, right before it hits the floor, it's right here. So now we have to call this the beginning of the problem. And now at the end is the final part. I need you all to visualize this, please. Forget the beginning of the problem. It's over, right? It's over. The beginning is done. So now this object has velocity right here, and it suddenly encounters friction. It suddenly encounters it. The initial velocity it has is the ending velocity from the last part. 1.37 is the velocity you got. That's the kinetic energy it has at this moment in time. Then at the end, it has no energy. So Q loss must have happened along the way, in order for there to be zero energy at the end. So when I think about a problem like this, I could say it had kinetic energy. So again, I'm kind of separating this as a new problem. It had kinetic energy, and it lost the kinetic energy to Q loss. Because at the end of the problem, it's going to stop, isn't it? You come across and slide and stop. You stop. I've got no potential. I've got no kinetic. I've got nothing. Where did it all go? It all went into the work done by friction. This is the word kinetic energy theorem. That's literally all it is, right? This becomes work done by friction. This is the change in kinetic energy. Why don't I have final kinetic energy? It'd be KEF minus KEI, right? If it was the word kinetic energy theorem. What's the final kinetic energy going to be? Zero. Again, this is the work kinetic energy. I want you to see that these are the same things. Because Q loss is work done by friction. And I could have put KEF over here. Take a look. I could have put it there. But you know what? It's zero, so it doesn't matter. So this becomes the work kinetic energy theorem inherently. And this is FD cos theta I can replace FF with mu Fn. I've done this now at least 5 times in this chapter alone. You've done it in your homework. You should be able to do that. I'm assuming you know this. This was from last test, and if you didn't know it then, you should know it by now. It's on your formula sheet. FF equals mu Fn. What's Fn in pretty much all of these problems? Fn is the force acting up to balance what acts down. On all objects, what acts down? The weight, which is mg. So Fn is in equilibrium with the weight, which is mg, or Fg, right? Which is mg. So I can replace Fn with Fg. But Fg is really m times g. So I'm like one step at a time replacing everything along the way. And the rest carries down. Okay? M's are going to cancel again. Look at that. So this is one of those cases that I was talking about where Q loss has an M in it and the M might cancel. Now, I want to continue. The question was to find D, which you can do now. U is given. VI, that's a VI. VI is given. Theta is 180, so you can find D, that's fine. But I want to go back for a second and ask you the following. If a problem directly tells you that the force of friction is 20 newtons, the force of friction is 20 newtons, where would that go in? Where would that go in? James, where would it go in?
The first line, right?
Yeah. It would literally go right here. You would put a 20 Newton in right here. You would put your mass in, which you know. You would put VI in, and you could solve for D. So if you're given the force of friction, you don't have to do anything. A lot of you confuse this on your lab. But if you're given the coefficient of friction, that's mu. Then you have to use this formula, plug mu in, that's 0.15. That's the coefficient of friction. It's usually a decimal, right? If I give you 50 newtons, that's not mu. That's FF. A lot of you confuse this in the lab. I just turned back. FF is a force of friction. This is mu. Then you got to go ahead and say, okay, am I given Fn? I'm not. I'm not given the normal force, but I got to realize that it's in equilibrium with the weight, and the weight is really just mg. James?
It's kind of off topic.
It's okay.
Do we have both 6-4 and lab 7 due tomorrow?
If you have not, yes, I think your section has both due tomorrow. That's correct. Yeah. Lab 7 you knew about, and 6-4 we had yesterday, but I gave you 2 days for that because the problem set was due today.
I just wondered.
Yes, I think they both are. Check Moodle. It's on there for sure. Yes?
So, the angle for cosine theta.
It's always going to be 180 for friction. Yeah.
Okay.
Yeah, and it doesn't matter because we're doing the absolute value, so this will become a -1, right?
Yeah.
And it'll just cancel out because it's absolute value.
Okay.
So it doesn't make a difference. But for this chapter, theta has pretty much always been 180 or 0. Unless I tell you, which we've done, that you're being pulled at an angle. And then if you're trying to find the work done, it's cosine of whatever that angle is. Yes. Chris?
There's a problem in the work where it just said it was like being pulled up. So you just like not move it.
Yeah, here's what's happening, Chris. If an object is here and it's moving up and it's being pulled up, what's the angle?
90? No.
It's the angle between those two lines. What's the angle between them?
Oh, 0.
0. Remember that theta for work is the angle between the direction of motion and the force applied.
Alright.
Okay, the direction of motion happens to be up here, and the force is also up. So therefore, the angle itself is 0 degrees. But you could have a problem like this, right? Watch. Imagine this is like a, kind of like a, I don't know, I'm trying to think of like a pulley system. So imagine that the rope extends this way, right? And the force you applied is at actually at an angle. That's a really bad example of drawing it. Let's say hypothetically, I know this is not correct, but you're pulling like that. So this force is at some angle theta. Well, here's the direction of motion up. The angle you're going to really use for theta is the theta in red. You see what I'm saying?
Yeah.
Because motion, this object, which way is it moving? Moving up. But the force is this way. The angle between them is in red. It's the red theta that you would use. The other theta in black is the complement of the one in red. 70-20, 60-30. Okay? Yes, Aiden?
Is it possible to do theta over 180 degrees?
No. No. Because at that point, you could just look at theta the other way and find the smaller than 180. But we won't have to ever see that in this section. Other questions? Do we understand power? What is power? The rate at which? What is power? I'm guessing the rate at which?
Change in energy over time.
Yeah. Energy changes or work is done, that kind of stuff. If you want to do more problems and samples after school, I'll be here. There's some extra problems on 6.3 under videos from class. 3 problems with video solutions. Feel free to look at those.
Are they gonna make a paint?
It could be anything what I should. Bring that to the lane. He gets
Dude, that's
it.
ridiculous. But it's not gonna happen immediately.
Hey, the lab will help you, so please do the homework tonight. The lab will help you with this.